So hey everybody, I'd love to introduce Phil Dennison from University of Utah, who's been, well, looking at vegetation from space across the entire world. You're welcome, Phil.
Great, thanks for the introduction, Greg. Thank you for the invitation to come speak this morning. I'm going to be talking about modeling vegetation cover at subpixel scales for the next generation of Earth remote sensing satellites. And I'd like to start off with a little bit of a brief look back at the history of Earth remote sensing. And a big step forward occurred in 1972 with the launch of the Earth Resource Technology Satellite, or ERTS, which was later renamed to Landsat 1. And it carried the multispectral scanner, which had just 4 bands. And these bands, 2 in the near infrared and 1 in red and 1 in green, with 60-meter spatial resolution, measured the reflected light off the Earth's surface, like the image you see to the right. That's showing an area of Chesapeake Bay. And this reflected light off the Earth's surface in these 4 wavelengths was measured using 4 different filters that filtered out those specific wavelengths. Landsat 1 started a nearly uninterrupted 53-year-long record now of recording change on the Earth's land surfaces. So a lot of the information we have about global changes like deforestation, urbanization, desertification, the retreat of glaciers comes from this really long time series. And if we look at the bands that have been measured over time, you can see that it's a somewhat limited view of the spectrum. So just to orient everyone as to where we are, everything on this side from 400 to 2400 nanometers, that's the reflected solar spectrum. So that's the reflected sunlight we're looking at off of the Earth's surface. And we do really well through time, from Landsat 1 going up to the current Landsat 8 and 9, looking at the reflected solar spectrum in the visible part of the spectrum, where we have blue, green, and red, and then going into the near infrared. So just that part that's right beyond the red. But then there's big gaps that we don't see with the Landsat series. And even when we go into the shortwave infrared, which is this part of the spectrum here, these 2 big bumps are what we would call in the remote sensing community shortwave infrared SWIR 1 and then SWIR 2. So in those 2 spectral regions, we just have one really wide band. And then as you go out even further for Landsat, we can measure in the thermal infrared. While the spatial resolution and the number of bands with Landsat has improved over time, the bands beyond the visible and the near infrared, particularly in that SWIR or shortwave infrared spectral region, have remained really wide, and they're few in number, and they haven't really changed much since 1982. It turns out that a few bands in the visible and the near infrared, which is where the strength of sensors like Landsat and Sentinel-2 is really at, it's enough to distinguish green photosynthesizing vegetation from everything else. And when we look at green plants, we notice they're green, and that's because of chlorophyll absorption. And so if you look in the visible part of the spectrum, so this 400 to 700 nanometers where we see, in the blue part of the spectrum, there's more absorption by chlorophyll. And in the red part of the spectrum, there's absorption by chlorophyll. And then there's this really steep thing called the red edge when we go up to the near infrared, and then high near infrared reflectance. That's what green vegetation looks like, photosynthesizing vegetation. And those bands, those 4 bands, are good enough to be able to distinguish the cover of green vegetation from things that have low green vegetation cover. If we take these 2 spectra, or these 2 curves, we can call them end members as kind of representatives of the extremes of either pure green vegetation or pure not green vegetation, which could be soil, it could be impervious surfaces like we have in urban areas. If those 2 extremes are end members, then any pixel could be modeled as a mixture between those. So you can imagine that we could have averages that might be 50% of the vegetation spectrum, the green line you see there, and 50% of the red line. And based on that type of mixing, we can use a few bands to model or decompose each pixel into a subpixel fractional cover of green vegetation that lies somewhere between those 2 end members. And as a result, for Landsat and for VIIRS and MODIS and for other sensors, we have a product that's called a green vegetation fraction. This captures the percent of green vegetation cover at different scales depending on the resolution of the sensor. And you can see an example in this figure where it shows higher green vegetation cover in the tropics and lower green vegetation cover at higher latitudes. Okay, so that's where we're at with those bands in the visible and the near infrared. And let's just look at an example to give us this concept of fractional vegetation cover. We can start off at high resolution where it seems to be obvious what type of land cover we have. So it seems to be obvious where we have green vegetation versus concrete versus asphalt versus some dried grass or whatever else it might be that's within our image. So this is something that might come from any of the high resolution sensors, either in space or on an aircraft. And if we were to decompose this image or average it out into a coarser spatial resolution, so do some spatial averaging, we would find examples of pixels in this image that were mostly pure. So we could look at, for example, this middle yellow circle and say, this is almost pure green vegetation. That's close to being one of our end members. So we could say that we could label that. But if we use a mixing model and say it's between those two end members, between something that's low vegetation cover and high vegetation cover, then we could decompose it to a fractional cover of 92% and say this is 92% green vegetation cover. This is a process that's being done for VIIRS, for MODIS, for Landsat, is coming up with this fractional green vegetation cover. We can also easily see places that have 0% green vegetation cover. And so here's an example. There's no chlorophyll absorption there. There's no red edge. We can say it doesn't have any vegetation. And then we can find some really highly mixed pixels that have contributions from each. So this pixel up here that I have in the circle might be modeled as 43% green vegetation. So this mixing model fractional cover is a very powerful concept as long as you have the spectral information to model the fractional cover within each pixel. That brings up the question of what about all the other stuff in the image? And especially one of the things that I'm really interested in is the yellowish land cover type in that magenta circle there. It's vegetation, but it's not green. It doesn't have chlorophyll absorption. It doesn't have a steep red edge. So it's a part of the ecosystem that we're saying isn't vegetation and that we're not modeling. And this turns out to be really important information to have, is where the vegetation is that isn't photosynthesizing, that is dead or senesced vegetation. And we have a name for this type of vegetation that doesn't have chlorophyll absorption and doesn't have a red edge, and we call it non-photosynthetic vegetation. And there are lots of examples of non-photosynthetic vegetation. I put a few up there. NPV is vegetative material lacking chlorophyll absorption and a red edge. It includes plant litter, senesced plant material, crop residues, stems and branches. It's a good way to think of it is the brown stuff. It's the brown vegetation. And NPV turns out to be really important. So seasonal increases in NPV are an indicator of plant senescence when gross primary productivity shuts down. It's an indicator of increasing wildfire danger. So you can imagine that grassy field there probably would not have burned 3 months prior to this when it was green, but now it's very susceptible to wildfire. Increases in NPV cover are associated with seasonal and long-term drought and plant mortality and disease and insect outbreaks and storm damage. So a good example in the lower left there is a forest that's been attacked by mountain pine beetle, and certain trees have been killed, and it produces a big increase in NPV, showing the extent of that insect outbreak. And this is something that we really commonly see with diseases in plants and insect outbreaks in plants, and not just in natural ecosystems, but also agricultural systems. And then finally, crop residue cover that you have up there in the upper right is an important indicator of erosion potential. And it also is important for indicating the tillage practices that impact soil organic carbon. So there's all kinds of reasons to care about this non-photosynthetic vegetation that we would want to model at a sub-pixel fractional cover level. Just to give you a couple of quick examples, what we might be able to do with satellite data. Here's a high resolution satellite image, and the yellow circle indicates about what a Landsat pixel would see. So about that equivalent area. And we might have areas that have higher MPV cover and lower fractional MPV cover, indicating the severity of the insect outbreak. Then we would have in areas that are covered by crop residues. These are really difficult. So if we look at the previous example, telling whether it's a red tree or a green tree, you don't really need a lot of spectral data to do that. You can do that in the visible and the near infrared. That's not too tough, but this is a challenging problem. Distinguishing everything that looks brown in the visible, soils and non-photosynthetic vegetation, they look really, really similar. But if you want to tell these apart, we don't have the spectral information really in traditional Landsat and Sentinel data to be able to distinguish these. And that's because most of the spectral information about non-photosynthetic vegetation and ability to distinguish it from soils is in that shortwave infrared part of the spectrum. And these plots show the SWIR2, and this is that part of the spectrum between 2000 and 2400 nanometers in wavelength. And in this part of the spectrum, the structural material plants, lignin and cellulose, absorb. If you look right here at about 2100 nanometers, you see a dip. And this is a absorption from the carbon and hydrogen bonds in lignin and cellulose that shows up in this part of the spectrum. It shows up again at 2300 nanometers. And it's really this lignocellulose absorption that's the hallmark of non-photosynthetic vegetation. Soil has all these really interesting absorption features that are really highly variable when you get out into the SWIR2 spectral region, are really useful for separating out different soil types. And you can see just with these different soil types where these different features occur at varying wavelengths, but there's a lot of variability there. Remember, with Landsat, we're only covering this entire spectral region with one really wide band. So there's really limited ability to distinguish these different materials and to say anything about non-photosynthetic vegetation. If we had the spectral information, this is what it would look like. So we do have airborne data, and these airborne data that I'm showing you right here are hyperspectral. Hyperspectral data or imaging spectrometer data have really narrow bands. And in this example, the bands are about 10 nanometers wide, and they're capable of resolving those absorption features. And these data cover from the visible all the way out into the shortwave infrared. And despite some of the issues of acquiring airborne data, it's not as regular as satellite data, but you can get some good airborne data at relatively high resolution. And when available, you can do some comparisons over time. And here is a model that I've done modeling the fractional cover of non-photosynthetic vegetation, shown in red, green vegetation with a chlorophyll absorption in the red edge, shown in green, and then soil, shown in blue. And you can see some pretty remarkable changes from April to June. You start off in April and you see higher green vegetation, fractional green vegetation at the pixel level. So saying sub-pixel green vegetation is higher. It's a higher percentage of each pixel. And then as you go into June, it goes more to MPV. So this big ring of grasses that you see around the Central Valley of California that was covered by the aircraft, you see it starting to turn to MPV. Lower down, a little bit higher up, more of it turns to MPV in June, and the change that you see is expressed here as an increase in MPV over that time from April to June. So you're seeing the signal of seasonal drought here. You've got some weird stuff going on with cloud cover in this one last line that was acquired in April, so that's why you have that strip there. But the other really interesting thing I want to point out here is the variability in cover in agricultural systems. And you see what looks like this patchwork starting in April, and you have areas that are green and blue and red. And then the same fields later on are different shades. And again, this is modeling the fractional cover of each component or each end member. And then you look at the change between April and June, and you see crops or fields that have gone from green to NPV, or from green to soil, or soil to green, and these transitions that occur with crop cycles happening throughout the year. And all of these are visible when we take this view of fractional cover, rather than just trying to classify a pixel as one thing. So this is a really valuable perspective. And this is where we want to get to for global monitoring, is to be able to do this on a global scale using data like Landsat. So this brings up some research questions. First question: what spectral information do we need to be able to model fractional cover of non-photosynthetic vegetation? And then 2, how accurately can we model GV, NV, MPV, and soil fractional cover using machine learning? We do have to go to a set of synthetic mixtures, because we just simply don't have the fractional cover field data to do this yet, especially on a global scale. There have been a few experiments that have gone out and measured fractional cover, but they're almost never at pixel scales, at the 10 to 30 meter scales that we need them at. So since those training data don't really exist yet, we are going to rely on some synthetic mixtures we're going to build from pure end members, and then model those mixtures. All right. Why is this important? There's help on the horizon for modeling fractional cover with future NASA missions. This figure shows NASA's Earth Science Fleet. There are 2 missions that are being developed that we're really excited about in the community that will revolutionize global monitoring of fractional cover. They're Landsat Next, which is the next generation of Landsat, and then one called Surface Biology Geology, VSWIR, which stands for Visible Through Shortwave Infrared. And that is going to be, both are going to launch somewhere around 2030 is the current projection, of course, dependent on budget and how the administration decides to invest the taxpayer dollars in these upcoming missions. Landsat Next will have 26 bands, 21 in the reflective solar spectrum, and 3 narrower bands will cover the SOAR2 spectral region. And the first analysis I'm going to show you today covers how we selected those 3 bands. SBG VSWIR is an imaging spectrometer, also known as a hyperspectral instrument. It will measure hundreds of narrow contiguous bands, and will do a really good job of distinguishing those absorption features. Okay, as I said, we don't have diverse fractional cover field data at pixel scales, so we're going to take pure GV, NPV, and soil end members that have been measured in the field using a field spectrometer like the one you see there. And we required a photograph of the field of view of what the spectrometer was looking at to be able to make sure that it was pure. Or a lab spectrum where someone has taken a sample into the lab and measured just that one thing. So we have our 3 end members there, and we can then determine mixtures, synthetic mixtures between those pure end members. We used 12 MPV end members that tried to characterize the range of different lignin and cellulose absorption features. They include conifer and broadleaf litter, senesced grasses, crop residues of varying types and moistures. And then we also included a smaller variety of green vegetation spectra. They just don't have the variability, the same variability in the SOAR2 spectral region. They're actually fairly boring in that region compared to MPV and soil. I'm showing you just the mixtures, or just the spectra here for the 2000 to 2400 nanometer range, but we did the entire spectrum from 400 to 2400. And then this incredible diversity in soils we had to characterize globally. There's a huge variety in soils, 48,000 lab spectra from different global libraries were taken and classified into 9 generic soil spectral types, and then we use a stratified random sample. And even then, we could only really get it down to about 228 different soil end members to fully characterize the full range of those different absorption features. And there's just so much variability in there. It was important that we tried to capture that global variability in soils.
So if you question about soils,
Sure.
are you thinking of like bare soils that are just directly visible, or like forest soils that may be covered? I mean, do you have any hope there?
Yeah, so it's in a fractional cover framework, then we're looking at what's on top, and we're not going to see what's underneath. Now, there is some scattering that occurs between a vegetation canopy and the soil that's underneath, and that produces what we would call nonlinear mixing. And that's something that's a little more difficult to handle. And I'm not really going to go into the details on how to do nonlinear mixing today, but it's not hopeless, but it's very unlikely that you'll see much on soil once you get canopy closure, for example. It's going to be a relatively minor component.
Okay, thank you.
Great question. Okay, so we created these synthetic mixtures, and in this type of framework where you have 3 things that sum to 1, fractional covers that sum to 1, it's really interesting for me for modeling, because you can't just use a plain random distribution like you might expect, because as soon as you determine the random value of, let's say, MPV, that constrains the random values of GV and soil, and you can't do them independently. So you have to use what's called Dirichlet function and then use the different weights in that function to determine how those mixtures are spread over that mixing space. So the triangle represents the different fractions of each end member. You can imagine the center would be an equal weighting, so 33% of each. And then depending on the coefficients you use in the Dirichlet function, you can have more weighting towards the center, more weighting out towards the edges, or what we went for was an equal weighting. So you're weighting all of the different fraction, or all the different mixtures equally. That means all the fractions aren't weighted equally. So you'll have a tendency to have lower fractions be more abundant for any single given end member. But overall, the mixing space will be equally filled in randomly by these mixtures. So we create 100,000 random mixtures of these end members. And you can imagine the number of combinations. There were 12 MPV and 228 soil, and then the 6 GV. So all of those random combinations, and then a random mixture. And then they were further randomly darkened using a scaling factor to approximate the distribution from Landsat 8. And then we added a Gaussian noise function based on what we would anticipate the signal to noise ratio might be for Landsat Next or SPG VSWR, the hyperspectral instrument. So that's our data set that we're going to deal with for the rest of today's talk, are these synthetic mixtures based on this assumption of linear mixing between these end members from those libraries. That first question, what spectral information do we need to be able to model fractional cover of MPV? Really focusing here on MPV because we do it so poorly currently using Landsat and other data. So we were given a budget of 3 bands, 3 SWR2 bands for Landsat Next to be able to estimate MPV cover. We started out by saying that there are millions of potential band combinations when you start to talk about an X band and a Y band and a Z band. So we started out by constraining it to just the SWR2 spectral region. We still ended up with hundreds of thousands of potential band combinations when you start to talk about different band widths, when you start to talk about band centers, and then how densely in space you want to vary those band centers. So a lot of complex modeling could have gone into it. We decided, given the hundreds of thousands of band combinations, that we would go with a linear regression between a variety of different metrics. So we came up with 4 different types of metrics for 3 bands and MPV cover, which again we have from those synthetic mixtures. The standard index forms that we looked at are not optimal for measuring absorption feature depth because they don't take into account the wavelength component of it. So we use this continuum interpolated band ratio, which basically interpolates to the green dot that you see. This green dot here is the interpolated value, interpolated average between the X and the Z band. So we're assuming that there's a convex hole around this absorption feature. And then you get the depth as the ratio between the Y band and that interpolated value. And then looking at many different possible band combinations, we also looked at some 2-band combinations. It turns out the lowest error comes in at 2030 nanometers for that X band, 2110 for the Y band, and 2210 for the Z band. And we refine this down even further for, this is at, I think this is at a 5 nanometer interval. We refined it even down further to a 1 nanometer interval based on these results, but we had to make sure that we got it right. So we needed to take into account some different factors. One is that the atmosphere absorbs in certain parts of the spectrum very strongly. Carbon dioxide is our worrisome gas here because of CO2 absorbing on either side of where that 2030 nanometer absorption is. It's really not optimally positioned. If 2030 is your goal, then you're going to end up with a lot of carbon dioxide absorption and a lot of uncertainty in your reflectance. So we went to radiative transfer modeling, and radiative transfer modeling models the transmittance of light through the atmosphere. Here's a few models with the atmosphere that when it's dry, on the drier side with less water vapor, and then that's the brown line, and then the blue line is with a wetter atmosphere. And we can see that if we average out over a wider number of bands, so out to 25 nanometers, that there is a narrow window there where we can get a good reflectance, a low uncertainty reflectance. And it happens to be right about 2038 nanometers as the band center with a 25 nanometer band width. And then that allows a little bit of tolerance for the manufacturing to be off by a couple of nanometers and still hit that window between carbon dioxide absorption. So that's the goal. We fixed the first band at 2038, and then we can run a 1 nanometer optimization to find out where the strongest linear relationship between an index is and the MPV cover. And we get to this Cindy index, continuum interpolated MPV depth index, and those are the bands and the coefficients used for that. So this allows us to move forward with Landsat Next, and Landsat Next will have these 3 bands. One big question that we had to answer is whether we'll lose continuity with Landsat Next or with the previous Landsat missions. And we can simulate using imaging spectrometer data what Landsat Next will look like. This is using the emit imaging spectrometer that's on the International Space Station, shown there in red. It has 7 nanometer wide bands, which are really good for simulating those wider 25 and 40 nanometer wide bands for Landsat Next. And it turns out that if we come up with a good model that takes into account all the spectral information, either in the Cindy bands or in the entire spectrum, then our residual reflectance is really, really low. So we should be able to do both new products with MPV fractional cover and a continuity reflectance for all the applications that rely on that old Landsat 8 and 9 band 7. So this is what it's going to look like. The blue bands are Landsat Next, and the gray bands are Landsats 8 and 9, and you can see how much better we're doing in the SWIR2 spectral region. We have really, really good resolution, spectral resolution for that lignocellulose absorption that you see for the red curve for NPV. All right, are there any questions on Landsat Next before I go on to the machine learning part?
Well, yeah. And so you covered the frequency space. What about the temporal space? How does that affect your ability to like the overflight kind of I guess, and also the angle, because you can also have on angle, off angle. How does that affect your quality analysis?
Yeah, so all of our spectra that we use for synthetic mixtures are from that nadir view or close to it, and that's because they're relying on field spectra. The bigger component that would be the more worrisome would be dealing with the BRDF, the bidirectional reflectance distribution function of green vegetation, because there's a big difference in how strongly backscattering vegetation is, green vegetation is, between the visible, especially red, and the near infrared. So we would see some differences there by view angle. They're going to be relatively minor, but I have to say that most data today that we're seeing from Landsat, the range of view zenith angles is small enough, maybe like plus or minus 7 degrees, that we don't see those effects, or they're now BRDF corrected. So MODIS, VIIRS, they're correcting to that nadir view, and it's not as big of a deal. Those are the initial products, the level 2 products that would go into a level 3 fractional cover product. And so we don't explicitly have to worry about that because of the BRDF correction that occurs.
Okay, and the overflight frequency, how does that affect your resolution, effective resolution?
Yeah, so for the temporal, Landsat next is going to be every 16 days, same as current cycle, but there will be 3 satellites, so that's going to bring it down to a higher cadence. And what we're expecting to see is the evolution of these mixtures over time. So, for example, currently you might have in March you might get 1 snapshot on your 16-day cycle with Landsat, and everything's green. And then you might have clouds at the end of March and then beginning of April, and then your next temporal snapshot might be in May. And by that time, there might have been a lot of change that occurred. So we're expecting to see much more subtle mixtures with this higher temporal cadence with Landsat next. Does it impact the modeling itself? Not likely, because our pure end members we know are all one thing. But we would expect to see more variability within that mixing space over time.
Got it. Thank you.
Okay. With the lines that you see, the spectra that you see there for MPV, GV, and soil, that's the type of spectral resolution that we will get with SPG VSWR. And indeed, these are from EMIT. So this is from a satellite or from the International Space Station. And you see this kind of detailed spectral information with all the spectral features. Green vegetation has a chlorophyll absorption. There's also liquid water absorption there that we can see. And then you see the lignocellulose absorption for MPV, an example of a soil mineral absorption, all very important. So we want to leverage the full spectrum. And our second question is, how accurately can we model GV, MPV, and soil fractional cover using machine learning? So we're trying to model all 3 now, and we're trying to account for that variability. Remember, we have a lot of variability in MPV and soil spectra, but just trying to get one fractional cover out of it. This is our exploratory phase here, the results of it that you're seeing in this table. So we're looking at different models. Landsat next is in blue, and SPG VSWR bands are in green, and then we have some field spectra that are not synthetic mixtures, but are field spectra that were measured, and then a subset was used for training and a different subset was used for testing. And the RMSE values that you see here are all based on the field data. So these are looking within that field spectrometer, that field of view, trying to determine how well we can model the fractional cover, knowing that we have that photographic information that tells us the exact percent cover of MPV soil and green vegetation. So going through some of the different likely candidates that we could use for modeling, we could look at random forest. We tried random forest at different trainings, using both the synthetic mixtures and the field data, using tuning and no tuning. We looked at XGBoost. We looked at partial least squares regression. We looked at Cubist. We looked at multiple end-member spectral mixture analysis, which is a fractional cover modeling method based on goodness of fit between the best fit spectrum of end members. Spectral feature analysis is based on the depth and shape of absorption features. And then Cindy is that index that I showed you from Landsat next. And you can see a wide range in RMSEs here, going from just over 15% all the way up to 23%. So some of these models are clearly doing better than others. We decided to focus on random forest because you can see that it tends to be at the top of the RMSEs there, so the lowest RMSEs.
So a question about RMSE.
Yeah.
So it's hard to know whether 50% is good, bad. Like what should be our intuitive scaling here?
Yeah, so lower is definitely better. This is going to be based on fractional cover. So you can imagine that if you estimate 30% MPV cover or 30% GV cover, it's going to be plus or minus that 15%. So that's pretty wide. We'd like to get lower than that, and I'll show how we do. But as a first cut, that kind of showed the way. Our ultimate goal is 10%. That's what the science community, including myself, have said that products would be really useful for all those applications dealing with drought, dealing with insect outbreaks, dealing with crop residue. If we can get it within 10%, that's going to provide some really, really useful products for the global community to use.
Got it.
Okay, so we're using random forest, separate models for Landsat next bands versus the hyperspectral case, which is SPG VSWR. And I'm just going to say hyperspectral from now on because it's a little simpler. The input variables included the individual band reflectances, spectral indices, principal components, and then metrics for the depth and shape of those absorption features that fall under the SFA spectral feature analysis scheme. We use VSWR for variable selection to down select from these hundreds of variables. And then we did some interesting modeling. There's separate models for the univariate case. So you can imagine one random forest model modeling MPV fractional cover for Landsat next bands, and then another separate univariate model for MPV cover using hyperspectral bands. But the really interesting thing about these synthetic mixtures and any mixtures is they have to sum to 1, and there's information there. If MPV is high, that means GV and soil should be lower. If GV is high, that means soil and MPV should be lower. So they're not really independent. And this is where we gravitated towards this multivariate random forest model, which creates a single model for multiple predicted variables. And the multivariate random forest models correctly predicted this sum to 1 relationship that was within the training data, which I thought was really interesting. They all sum to 1 in the predicted fractional values when you're looking at MPV, GV, and soil. Okay, so we tuned both the univariate and the multivariate. Didn't change the outcomes that much, but this is what the variable importance looks like. It's going to be really hard to see these variable names, so I just want to give you the big picture, what's important here. The univariate models primarily use variables that were directly related to each cover type. And what you can imagine for green vegetation, this is going to be related to chlorophyll absorption variables or near-infrared red edge absorption variables. Those are the signatures of green vegetation. For fractional MPV cover, the univariate model is going to use lignocellulose absorption and other metrics that look specifically at that part of the spectrum. The really cool thing about the multivariate models, both for the multispectral Landsat next case and the hyperspectral case with many, many bands, for the multivariate models, the metrics for each of the different fractional components show up in each of the fractional models. So for example, the GV model might have metrics for MPV and soil that are related to the expression of lignocellulose absorption and soil features. The MPV metrics for the multivariate models, they include green vegetation signatures. So for the multivariate model, it's as important to define what the synthetic mixture is not, in addition to what it actually is. So I think that's one of the really fascinating parts of these multivariate models, is it takes a much more holistic view of the spectrum, trying to define all the different features together, rather than just taking a look at lignocellulose absorption on its own or chlorophyll absorption on its own. And indeed, when we do look at the parts of the spectrum that are selected for these variables and weight them by their spectral importance, what you'll notice is that the dashed lines are higher in different parts of the spectrum that are not associated with the specific absorption features for that particular material. So for MPV especially, it's a good example looking at MPV showing for both the Landsat Next and the hyperspectral cases, it does incorporate information on green vegetation. Same thing goes for soil. There's green vegetation spectral features in the soil multivariate model that don't show up in the univariate model, whereas the soil absorption features are, their significance or their importance is diminished when we get into this more holistic multivariate model.
So just to understand what you're showing here, these are, you trained, it looks like 3 separate random forests. Each one of them was supposed to predict the fraction of that is, let's say, GV, but implicitly the fraction that is not GV. And that differentiate, and you're not yourself forced it to add up to 1. That's just something each model had to kind of pull off.
Yes, yeah. And I'll show when we add up all the fractions from the univariate models versus the multivariate models, how you get this spread for the univariate models, because there's no constraint there that's trained. There's no training information that says these have to sum to 1.
Right.
But with the multivariate model, they always sum to 1. They're right on that 1 line.
Got it. Thank you.
So here's the results on the training data. And I just want to point out the big important thing here is that green vegetation is much easier to distinguish from soil and MPV because of the chlorophyll absorption and the red edge. And that's where we started off this talk, right? We said that it's pretty easy to tell GV from other things. There's more spread for soil. But what you will notice is that we do have pretty comparable accuracy between the univariate models and the multivariate models. There's not a big difference in spread there. The root mean square errors are pretty similar. Hyperspectral is a little bit better, lower RMSE, but there's not a big difference there in spread. But we do want to bring in some independent data for testing. And this is where we rely on those field data. Here's an example for a field with some crop residue. And then the photograph can be used to give us percent fractional cover. Okay, what we have here is our, this is our models applied to the field test data. And this is showing where we don't have that uniform abundance. So we don't have the uniform mixtures throughout that mixing space. We do have many more mixtures that have 0 of something. So 0 soil and higher MPV and GV, or 0 GV and higher MPV and soil. So that's something that we haven't really accounted for in our training data. But we still see pretty low RMSEs that in the MPV range are somewhere down in the 11 to 12% range. So we're getting pretty close, even down as far as almost to 10% for some of our models, definitely for GV. Soil is the hardest, and it has the highest RMSE. This is by no means a comprehensive test data set, but it tells us that we're headed in the right direction. Now, this is showing when you sum up those fractions. When you sum up the fractions, what you end up with is a spread in the validation data for the random forest, the univariate random forest, that is interquartile range. It's not that big. So we're talking about something in the 3% range. But then when we apply it to the test data, it really widens out. So this sum to 1 seems to be, with multivariate random forest, really seems to be the right direction, because I can imagine if you are are using an application of these fractional cover data, and you get to 120% when you add up everything, or you only get to 60% when you add up everything, that's going to be really hard to use in an applied sense. So I really like this direction with the random forest that uses the multivariate modeling. Okay, so just to wrap up the next steps for Landsat Next, these 3 bands in the SOAR2 there that you see, 19, 20, and 21, have been adopted into the design specs. You can see where all 26 of those bands fall, 21 in the reflective spectrum. And this is really going to revolutionize our global monitoring of vegetation cover, being able to include NPV. And then when we go to SBG vSWR, we're going to see this really detailed spectral information like the spectra that you see there, which should be able to give us even higher accuracy. And if everything works and goes up, then we'll have 4 satellites that are at the same time looking at the Earth's surface, giving us a really high temporal cadence to being able to look at fractional cover changes that might be associated with drought stress or insect infestations or whatever else we might see. We really need better field data, and this is where we're hoping to make a push in the next several years if funding allows. And this is where we're going to be taking drone data at 1.5 centimeter resolution and then classifying it as different cover types using convolutional neural nets, ending up with a fractional cover of non-photosynthetic vegetation, green vegetation, and soil. We can then sample that up to the 20-meter resolution of Landsat Next, compare it to airborne or satellite hyperspectral data where we can get limited areas of those hyperspectral data, and then create these machine learning models using multivariate random forest. And then, of course, looking at air propagation as well. So this is our goal. This is what we're hoping to do over the next few years. So far, this is looking promising in just some of our preliminary data. A shows a drone image at 1.5 centimeters. C shows a classification into 3 different classes. E shows that NPV cover at that Landsat scale. And then we can take that convolutional neural net, apply it to an entirely different image in an entirely different location, and see how well it does. It doesn't do as well as if we had trained that specific image B, but it does a reasonably good job. And so we can look at how well these neural nets then, how well they can classify in different ecosystems, the fractional cover, and hopefully come up with a more generic CNN that would allow us to have the best estimates across a wide range of ecosystems at that 1.5 centimeter scale of these fractional cover types. And then sample that up to Landsat Next. If we get funded, we'll be looking at these sites where we know we'll have hyperspectral data over the next 2 to 3 years, and that we would be able to get that information. The areas in yellow are being flown with hyperspectral for mineral exploration. Of course, rare earths being very important. There are some fingerprints out there that they'll be looking for. All right, so looking into the future, the combination of Landsat Next and SBG vSWR are going to provide this unprecedented spatial and temporal coverage for mapping fractional cover. The big pushes will be in field data at scales useful for satellite remote sensing, better understanding scales of variability. So one thing I didn't go into is that mixing is going to occur at all scales. We can't even assume a 1.5 centimeter pixel is pure, because when you're looking at vegetation or any type of ecosystem, there's mixing that occurs at even the finest microscopic scales, at millimeter scales, at centimeter scales, meter scales. Mixing really occurs at all levels. We have to ignore some of it to be able to scale up, but understanding how it varies with scale is really important. Better understanding some of the nonlinear mixing impacts as we get to higher and higher vegetation cover is important. Modeling mixtures containing additional cover types like water and snow and impervious surfaces. We want to look at those too, and then development of the algorithms that can turn these into global products for monitoring things like drought stress, fire danger, insect outbreaks, and crop residue cover. If the resources are there, we'll be ready to go when Landsat Next launches, and we'll have NPV cover products shortly after launch as soon as the data start streaming down. That's the hope. That's the vision. So with that, I'll end, and I'll take any questions you have.
Well, excellent. Thank you very much. One obvious one is you've been talking about a lot of spectral information. What about LiDAR, SAR, any kind of like elevation? To what extent is that complementary to this the data?
Yeah, we look at a lot of LiDAR data in my lab, and it's really interesting. They're complementary, but we have to be really careful when we get into LiDAR data because the dead stuff sticks around a lot. When we're talking about dead forest canopies and we do a canopy height model, we find that we see the forest height regardless of whether it's live or dead. We don't know whether it's live or dead until we look at the optical data. And whether that's high resolution or, maybe we get fractional cover from Landsat, we won't know just based on LiDAR alone because much of the standing structure remains there and still reflects the LiDAR data or the LiDAR pulse and gives you that structural information. But that gives you important information as well. So that would be an additional piece of information that could help with distinguishing MPV from soil. Because soil isn't up in the air. It doesn't have that same structure as dead vegetation does. So at least in places like shrublands and forest, it would further be able to refine MPV cover because MPV cover alone will have that vertical structure, whereas soil will not.
So is there a notion of, I want to say spatial roughness? I guess what I have in mind is a lot of analysis is this pixel looks like this, therefore is this category. But this neighborhood and how much it varies is also an indicator. I'm thinking separation due to river channels or forest fire means a lot of sticks sticking up in the air with nothing between them, a different spatial roughness. To what extent is that usable?
Yeah, it's likely usable to some degree, but we want to get away from calling a pixel one thing. And that's the whole goal of the fractional cover. So we would be able to decompose it into fractions from that top-down view. That doesn't mean that there isn't a lot of like dead standing biomass there, for example. You might have many dead trees that are standing there, but from that top-down view, we'll see the spatial coverage of that non-photosynthetic vegetation. Does that answer your question?
Right. And but I'm trying to figure out like one kind of machine learning that's emerging right now. I'm thinking foundational models, and they have the ability to. What do they do ultimately? Any one of these LLM kind of things, you rip out a sentence, rip out a chunk of picture, reproduce it from the surrounding context. So now you say, if the surrounding context is burned down, odds are this is burned down kind of thing. Or this side is burned out and there's a river, then the other side, well, different distribution, but region matters. And the climate matters at the time and so on. So now it's not just the pixel, it can be fractional, but how does one pixel fit into the spatial temporal environment?
Yeah, and that's super important, and we haven't gotten there yet. So I'll be honest with you. In the remote sensing community, our modeling hasn't really taken into account both the spatial component and the fractional component at the same time. It has been done certainly when you're looking at continuous pixel values and then in a discrete value for a pixel. But I can't think of anything that I've seen that has explicit spatial structure and fractional cover, where you have multiple components within the same pixel. And especially, I think it would be important to look at that, again, that sum to one is something that's going to be interesting area for exploration, whether that constraint can be maintained in some different modeling frameworks.
Okay, that's really valuable. And then, so I'm thinking the difficult questions to answer from satellites. There's the obvious ones, I mean, vegetation and crop type, but when it gets nastiest, I think, is when it's pests. This thing is slowly dying due to something and vaguely changing colors. And to what extent is our pest infestation detectable now? And to what extent do we need additional satellites for that?
Yeah, it's a great question. One thing that we're really interested in looking at is that some early signs of stress that might show up before the lignocellulose absorption shows up. So if we're looking at this at our end member spectra here, the important spectral features that we would start to see a shift in as a plant starts to weaken but isn't dead yet would be a shift in the red edge. So it can start to flatten out, but also shift a little bit. So this portion here, so the wavelengths can subtly shift and the red edge can start to decline a little. That's an often subtle signal. And then this canopy water absorption up here, so this feature, and then as you go a little bit over, this feature here, that's liquid water absorption within vegetation canopies. And if a plant stomata close and it starts to really be drought stressed, and then it's not drawing up as much water from the soil, it's starting to shut down. We think there would be some initial signs there. So if you're just starting to look for those weakest initial signals, it's going to be an alteration of the green vegetation components rather than seeing that lignocellulose absorption show up immediately.
But this bit looks like no satellites. It's covering that region.
The imaging spectrometers, the hyperspectral sensors are, we just don't have the regular the acquisitions that we do with Landsat. So the Landsat Next will have a red edge band, and it will have a liquid water absorption band that you can see there in blue. So that spectral information will be there. But right now we have EMIT on the International Space Station. Planet has their new Tanager imaging spectrometer, but those are going to acquire small areas. And so to get to this, truly regional or global monitoring, we're going to need better data.
Okay. And then maybe last question is things like crop yield, the true amount of biomass. In fact, I mean, tree yield as well, but crop yield probably has most economic and the most diverse kind of application.
Yeah, that's not my area of research, but I do know that that there are models that take into account spectral information, and particularly using the full spectrum is the most robust approach to that. So the more spectral information you have, the easier it is to predict things like yield and biomass. Not all biomass can be predicted using optical data, though. That's where LiDAR really shines as things get taller. Certainly for crops, it's going to be easier because your stature's lower, and LiDAR is not going to provide much information there, but you can see the strength of chlorophyll absorption and liquid water absorption that would give you some indicators of yield. But especially for a forest, I think for biomass, you're going to be much better going with LiDAR if you want to get that true measure of height related to biomass.
Got it. Well, yeah, thank you very much. This was very valuable.
Yeah.
Yeah, have a good day. Thank you.
Great. Thank you.